All right, so we're gonna finish up this week looking at section 4.4. Okay, we're gonna do 4.4 part 1 today, and we'll do part 2 tomorrow. So what we're gonna be looking at are what are called radical functions. Okay, so radical functions are basically anything that has some type of root in it. It can be a square root, it can be a cube root, but it has to have a root. The simplest radical function, I didn't write it down, but would be this one. Okay, square root is one of the most common roots we deal with. And this doesn't have any other numbers with it. Okay, I'm not adding the numbers, subtracting, multiplying, just a square root of x. Okay, we are going to do the same thing we did with other functions. Okay, we will look at transformations eventually. So like shifting it left and right, shifting it up and down, stretching it, flipping it. Okay, we'll do all that. We're going to look at solving equations. So I'll give you a problem and we got to solve for x. We'll also look at just sketching, right? Making a sketch of these pictures. So those are generally the three things we do with every function we study. We learn how to solve it, sketch it, and transform it. All right, so what I want to do first is just kind of go through some vocabulary so we know when I talk about certain parts of these expressions, I can use the proper word and you know what I'm talking about. So the first thing is this number that you put on the outside of the root right here, that is called an index. The index has to be a number bigger than 1. And it has to be, it can't have a decimal. It has to be an integer. So you can put a 3 for the index. That would mean you're doing a cube root. You could put a 5, and that would mean you're doing a 5th root. But what you can't do is put a negative number, a 0 or a 1, and you can't put a decimal. There's no such thing as like a 2.3 index. You can't do that. This entire thing that I just circled, that's called a radical, or you can also say radical expression. It's not a radical equation because this doesn't have an equal sign. Right? So that's a radical expression. This part right here is a radical expression. This entire thing is a radical equation. The part that is underneath the root, so like in this problem right here, just the x minus 2, that's called the radicand. It's just the part that's underneath the radical. This symbol is just called the radical sign, or you could call it the radical symbol. Okay, so a radical equation is made up of several parts. It has a radical expression. In that expression, there's an index and a radicand. Okay, so those are some different terms that we'll be using. Any questions on those terms? So let me just write something down. And if I said to you, what is the radical equation that I wrote on the board? Somebody just tell me what that is. What's the radical equation that you see there? Yeah?
The whole thing.
Yeah, the whole thing, right? Y equals the 4th root of 3x minus 5. That's the radical equation. What's the radical expression there? I said to you, just tell me the radical expression that you see. Yeah?
3x minus 5 under the radical
Yeah, so that's the 4th root of 3x minus 5. Okay, so there's no powers there, right? That 4 is not an exponent. What is the 4? It's the index. Yep, so 4 is the index. And then what if I just said, what's the radicand? from what you see on the board. 3x minus 5. Yep. Okay. We can write a radical symbol without an index. If you write something without an index, we always assume the index is a 2. So if you write something like that, we're dealing with a square root. If you want to deal with a root that's anything other than 2, you have to put the index. You could also put the index when it's a square root. That means the same thing as that. It's not very common to write it the way it is on the left. It's usually just written the way you see on the right. Now, when you're doing a radical, there is another way you can write it if you don't want to use the radical symbol. So if I take the square root of 16, what will I get when I hit enter? 4. I could also take 16 and raise it to a certain power and also get 4. Does anybody know what power I could raise 16 to? And I would get 4 as the answer. No, not a quarter, but you are on the right track with a fraction. It's definitely a fraction. With a 1/2, yes. So taking a square root is the same as raising something to the 1/2 power. Here's another example. How about if I did a cube root? Anybody have an idea what power could be represented by a cube root? 1/3, yeah. So if we try that on the calculator, if I go to math and I go to option 4, that's how you can do a cube root. And if I type in 8, the cube root of 8 is 2. Now let's take 8 and raise it to the 1/3 power. 2. Yep. How about if I did a 5th root? What exponent do you think would be the same as a 5th root? 1/5, yeah. The pattern is it's 1 over the index. Now, this last one is the real reason why we might change something from having a radical symbol to having an exponent. What we have here is a power raised to a power. Does anybody remember when you have a power raised to another power, what you do with these two powers? You multiply them. So that would be 3 to the 8th. Okay, we can do the same thing here. What's 4 times 1/5? 4 over 5, yeah, 4/5. Okay, so that's where changing a radical to an exponent could come in handy. You can simplify a power to a power. These other two, you might think, well, wait, do we have a power to a power here? No, not in this middle one. Once you add or subtract something inside, then that messes up being able to do what we just did right here. Okay. You can only do what we did here if this is a single term, no plus or minuses in the radicand. Then you can simplify a power to a power. All right, so let's look at what it means to solve an equation for the principal root. First thing to understand is when you are dealing with roots in general, there is more than one answer. If I type that in on the calculator, it will just give me one answer. What's the answer the calculator is going to give me to that? 5. Because 5 times 5 is 25. But there is another number. What's the other number that you can multiply by itself and get 25?
-5.
-5. We can check it by doing 5 squared. Yep, that gives you 25. And negative 5 squared. That also gives you 25. When they ask for what's called the principal root, they want a single answer. And I'm going to show you which one you're supposed to give me. Should you give me the 5 or should you give me the negative 5? Well, we're going to break it down into different cases. Okay, the two cases we're going to break it down into is whether that exponent is that index is an even number or an odd number. Let's start with an odd. So let's say that I had to explain to somebody how to do an odd root. Let's do a cube root. And somebody's never heard of cube root before. Okay. This is how I would explain it. All right, so cube root. Say I gave somebody this question and they've never seen cube root before. I would say, all right, what you're trying to do is you're trying to find some number that you can raise to the third power and it will come out to 8. Okay? You're basically trying to solve that equation. This is what was by itself right here. This exponent was the index, and this number on the other side is what was underneath the root. That was the radicand. So cube root of 8 means, can you find a number raised to your index that will give you the number that was under the root? That's how you think about doing an odd root. Okay. So in this case, what number could you raise to the third power and get 8? 2. Yeah. So, and if you're not sure how to solve it, you could do it on the calculator. But that's the idea of how you do an odd root. Right? If it said 5th root of x equals 13, right? That's a little harder to do in my head. I'm not going to be able to do it in my head. But what I would be thinking about is there a number I can raise to the 5th power? Whoops, actually, let me write that a little differently. Let me switch those two. Is there a number I can raise to the 5th power that would give me 13? And it would be somewhere between 1 and 2. 2 to the 5th power is too big. That's 32. But 1 to the 5th power is too small. That's only 1. So I'd have to use my calculator to figure that out. Bless you. Now, how about if I had something like, let's say, cube root of negative 8? Is there a number you can multiply by itself 3 times that would give you the same number that would give you negative 8? Yeah, negative 2. So the point here is when you're doing cube roots, you can either have a negative number under the root, or you can have a positive number. You can take the cube root of anything. Positives, negatives, zeros, fractions, decimals. Okay? Cube roots work all of the time. Any odd root works all of the time. 5th root, 7th root, doesn't matter what you plug in. It can be positive or negative. Now, let's compare that to an even root. First of all, when we're dealing with even roots, I'm always going to make sure that I give you a problem where the radicand is 0 or higher. Why do I want the radicand to be 0 or higher? Think of like a square root. What would happen if it wasn't 0 or higher, and you try to take the square root of it? Yeah?
It's impossible to get a negative to square it and then to get positive. Or it's possible to square a number and then have it be negative after being squared.
Okay, so with most numbers, you can't square them and ever get a negative, because squaring means you either multiply a positive times a positive or a negative times a negative. In both cases, that's always positive. But what kind of numbers can you square and get a negative? It would have to be what? Yeah?
Imaginary
It would have to be imaginary. Okay, and we're not dealing with imaginaries. So that's the very first thing. When you're dealing with an even root, square root, fourth root, sixth root, you need to make sure that this number is always 0 or higher. It can be 0. No problem with 0. Square root of 0 is 0. But it can't be negative. Once we make sure that that happens, then you're basically solving an equation, just like we had before for odd roots. Right. So let's say somebody's never seen square root, and I asked them to figure that out. I would say, all right, square root means your index is what's your index on square root? 2. Square root means that there is some number you can raise to the second power and you get an answer of 16. If you can figure out what number times itself gives you 16, then you know how to do a square root. Now, we just said there are 2 numbers. You could multiply by itself and get 16. When I ask you for the principal root, I want the answer that is not negative. Okay? Not negative. So what would you tell me that the square root of 16 is if I asked for the principal root? 4. Yep. 4 would be the answer. Okay. Any questions on that? All right, so now let's see what happens when we take some square roots. I want to see if when we take a square root, does it get smaller or does it get larger? And you see what I did with the font there? Smaller is smaller. All right. So let's try 4. If we take the square root of 4, what do we get? Let's say principal root. 2. Is that smaller or did it get larger? It got smaller. All right. Let's try another one. Okay, this is not a perfect square, so let's just use the calculator. Square root of 18. Well, that got smaller again, 4.24. So it seems like, at least with the examples I've done, when you take a square root, it gets smaller. Can anybody think of a number you take the square root of and it doesn't get smaller?
A fraction.
All right, we're going to talk about fractions in a minute. Something's going to happen in those. But how about something you can take the square root of and it stays the same?
0.
0 or 1. Okay, if you take the square root of 0 or 1, it stays exactly the same. So from those examples, it looks like when you take a square root, maybe it either stays the same or it gets smaller. Well, let's try taking the square root of 0.5. Okay, that's a fraction, right? 1/2. I got 0.71. What happened that time? It got larger. So the answer to the question, when you take a square root, does it get smaller or does it get larger? Or does it stay the same? Well, it depends. It depends what kind of number you plug in for the square root. Okay. Any questions on that? Okay. So let's graph an even root and an odd root. And I just want you to kind of see the difference between the two, and I'm going to show you how you type in roots. Okay, let's do a square root. You have a button for that one. And now let's do a fourth root. There is no button for fourth root. The way that you type in a root that you don't have a button for is start with the index. So I'm going to do a fourth root. You press math, and then you pick option 5. And that's how you do a fourth root. Okay, I'll also do a sixth root. So you press 6, math, and then the fifth option. That's how you do a sixth root. Okay, so let's graph. These are all even roots. Square root, fourth root, sixth root. Let's do zoom 6. And let's see what they look like. All these roots are going to look, at least all even roots, they have kind of a similar look to them. First of all, they're only in quadrant 1. Now, I could shift it left, right, up, or down, and I could bring it into another quadrant. But if you don't shift it or do anything to it, that's pretty much what an even root looks like. It starts at the origin, and it curves to the right. Because it starts at the origin, I want to zoom in a little bit. Now that we know it doesn't go in quadrants 2, 3, and 4, I'm going to zoom in more on quadrant 1. So there's your square root. There's your fourth root. And there's your sixth root. Does anybody notice anything about all those roots? Something they might all have in common? Okay, so they all have a similar shape. They kind of start at a point and curve to the right. Where does it look like they all start from?
0.
Yeah, it's a little weird with the coloring here, but they do all start at the origin. Yep. Is there anything else that it looks like they all have in common?
From 0 they go up.
Okay, so they all have a positive slope, curving. It's curving up and to the right. Anything else they all have in common?
1,
What do you mean 1?
1, 1.
1, 1, yeah. All even roots, if you don't shift or stretch them, will go through the point 1, 1. Just think about what's the square root of 1? 1. What's the fourth root of 1? 1. Okay? All even roots go through the point 1, 1. So let's write those facts down. Okay, so looking at even indices, we can see they all kind of have that same look to them. Okay, what I want to do now is graph some odd ones. Okay, big difference between even and odd. Even, it's only going to go in one direction. Let's try some odd ones. If you already have a root typed in, you don't have to go back through and do the index all over and do math 5. You can just highlight that index and just change it to a different root. So now I'm going to do a cube root, and I'm going to do a fifth root. Okay, I'm only going to do 2 odd roots, just because I want you to see the general look. So notice big difference. They go left and right. They don't just go in one direction. Okay, let me zoom in a little bit more, okay, so we can see it better. Let's do like -4 and 4. Now, one thing you might notice towards the origin, it gets a little steep. So it almost looks like the graph disconnects. It shouldn't look like that. Let me put this up first, and then I'll let you copy that down. So it looks like it's almost disconnected, but these are continuous, meaning you never have to lift your pencil from beginning to end as you draw it. They go in both directions, and they each have 3 points that are common to all the graphs. They all go through the origin. Does anybody see another point that 1, 1, and -1, -1? Now, we're talking about an odd root that you haven't stretched or shifted in any way. If you shift this up or down, then yes, you're going to change all these points. But if you don't shift it, stretch it, and you just graph the basic function, these rules that I just put on the board will always apply. They will always go through the points -1, -1, 0, 0, 1, 1. And unlike the domain and range of even roots, which basically started at the origin curved up. So it only went to the right and up. That's why the domain and range don't include any negative numbers, because it doesn't go down here. Odd roots too. Okay. Odd roots will go left and right forever, and they will go up and down forever. I know it kind of looks like this root is leveling off, but it never does. It keeps slowly dropping down, okay, forever. So odd roots, the domain and the range is all real numbers, which you can write as negative infinity, comma, infinity. Okay. Any question on that? Okay. And that's just the picture. Is there any question on how you type in a root on the calculator besides a square root? How you do the index, math, and option 5. For cube root, you technically do have there is a menu option for it. So you can go to math and press 4. But any other root besides cube root that's higher, there's no option for it. All right, let's look at transformations. Okay, so we told you every function we've done, we've looked at transformations, and transformations are going to be exactly the same. All right, so what I want to do is put that template on the board, but I want to give some more space because I want to describe what the A, the B, the C, and the D are going to be doing. I didn't put a specific index in because this can apply to any index. Square root, cube root, fourth root, that index doesn't matter. Okay, so let's start. When I talk about inside the function, I'm talking about the radicand, okay, the part that is underneath the radical symbol. Does anybody remember when you add or subtract, is that a stretch or is that a shift?
Shift.
That's a shift. Okay, so adding and subtracting is a shift. So both A and D are going to be shifts. One's horizontal, one's vertical. Anybody have a guess which one A is? It's inside the function.
Horizontal.
That's horizontal. Yep. And everything about horizontal transformations is backwards. So if you have a plus, which way do you think plus is going to shift your graph?
Left.
It's going to shift it left. And a minus?
Right.
To the right. Okay, that's what A is. Let's look at B. B, like A, is still inside the function. But now it's multiplication instead of addition or subtraction. What kind of transformation is multiplication? Yep.
Stretch.
It's a stretch, and it's still inside the radical, so it's going to be what kind of stretch? It's going to be a horizontal stretch. Okay, so we've got horizontal stretch. Let me give you a couple examples because B it's also backwards. Let's do an example where B equals 3. If B equals 3, you might think, oh, it stretches it 3 times as big. Nope, it actually makes it 3 times as small. So we would say this is a horizontal stretch by factor of 1/3. It actually compresses it 3 times as much. If B was a half, okay, you might think, oh, a half. It's a small number, it's going to make it smaller. Nope. Small number actually makes it bigger. So if B was a 2, this would be horizontal stretch. I'm sorry, if B was a half. It would be horizontal stretch by factor of 2. That's what B is. All right, let's look at C. So C is like B, it's multiplication, but now it's on the outside. So any guess what kind of transformation C is going to be?
Vertical stretch.
It's a vertical stretch. And once we do the verticals, there's nothing backwards about them. Okay, they do exactly what you see. So I'll just do one example. Let's say C was 2. You would say vertical stretch by factor of 2. Okay, so that's what C does. And the last one is D. D is addition or subtraction, and it's like A, but on the outside. So what kind of transformation do you think D is? Vertical shift. Yep. And there's nothing backwards about it. Positive is up, negative is down. Okay. So that describes mostly what the ABCD do. There's one more thing we have to mention, and that's if the B or the C was a negative. Does anybody remember what happens when you to your graph when you multiply by a negative number? It flips it. Yep. So I'm just going to say if B is negative, that's going to cause something like this. B is a horizontal. It causes a horizontal reflection. This is a horizontal reflection, left to right. That's over the y-axis. So if B is negative, we're going to reflect over the y-axis. What do you think would happen if C is negative?
Over the x-axis.
Yep. So I'm just going to put if C is negative, reflect over x-axis. And the reason it's over the x-axis is because C is a vertical. Vertical reflection means you're going to flip, or vertical flip up to down. So this would look like that. That's a vertical reflection. That's over the x. Okay, so that page right there describes all the transformations of a radical function. Okay. Any question on anything about the A, the B, the C, or the D? All right, so let's try a couple of these, and then I think that might be a good place to start. So it says explain how to sketch the square root of x minus 2. First thing is you're always going to be comparing roots with the same index. You're never going to compare a square root to a cube root. It's literally like comparing an apple and an orange. They're totally different. You're only going to compare the same root to the same type of root. So we've got a square root and a square root, and that's our transformation. What is happening to this to change it into that?
Shift 2 spots to the right.
It's going to shift 2 units, and if we're not sure, we can go back and look. It's got a minus. Minus means it shifts to the right. Yep. So shift 2 units to the right. try this one. How about h of x, the square root of x plus 3?
3 units to the left.
That's taking the base graph, right? That's the starting point, and moving it 3 units to the left. Okay. Any questions on that one? So those are two problems that each had a single transformation. Let's look at one that's got a little bit more, but I'm going to change this. Let's do that. Okay. First, how many transformations are happening in that one? 5. There's a total of 6 we could have. There's 2 stretches, 2 shifts, and 2 reflections. Okay. We have 5 out of the 6. When you describe the transformations, make sure you describe them in the order A, B, C, and then D. Right. If you want me to be really clear, I can just write them down. So first transformation is always the horizontal shift. If you have it, then you describe the horizontal stretch. If you have it, these are all if you have them. Then you describe the horizontal reflection. Then you do the vertical stretch. Then you do the vertical reflection. And then you finish up with the vertical shift. Okay. So if you're mapping that to the different letters, this one comes from A. These both come from B. These both come from C. And the last one comes from D. So I went right in order. A, B, C, and then D. Okay. So we got 5 transformations. Let's start with the first one. What number are we going to focus on first there?
6.
A -6. Yep. What does a -6 do?
6 units to the right.
It's going to shift 6 units to the right. Okay, so we dealt with the 6. What's the next number we're going to look at? The 3. Yep. Which actually in the example I gave you, it actually is a 3, so we can just read that off. What's the 3 going to cause the graph to do?
Horizontal stretch by a factor of 1/3.
Right. Horizontal stretch by factor of 1/3. Okay. What's the next number we look at?
Negative.
Not yet. Negative is going to be step 5. We still have something to look at in step 4. So what number there? The 5. Yeah. Just looking at the 5. What's the 5 do? Vertical stretch. How do we say that one?
By 5.
By factor of?
By factor of 5.
By 5, yeah. So vertical stretch by a factor of 5. And
Vertical reflection.
next one now is the vertical reflection because we have the negative in front of the 5. So we can say vertical reflection, or you can also describe it as reflecting over the x-axis. You can also say flip over the x-axis. And what's our last transformation?
We're going to shift up 7.
Yep. So then we're going to shift up 7. Okay. Any questions on describing the transformations?
If the 3 was negative,
Mhm.
then there would have been another step.
If the 3 was negative, then we also would have had this step right here.
Yeah.
We didn't have that step in this problem. Yep. Any other questions on that? All right. So we're going to look at sketching tomorrow, and then we'll look at solving radical equations tomorrow. And that'll be it. All right. So let me. I gotta adjust that a little bit. Okay, so homework tonight is on page 255, and it's numbers 1 through